Imagine for a second that you stumble across a set of ancient cryptic blueprints. You unroll them, and as you study this incredibly complex geometry, you realize they aren't for a building. They're instructions for how to build a human mind. Then, you flip those blueprints over, and you notice something basically impossible. Those exact same lines, those exact same mathematical ratios. They are also the structural schematics for the interior of a black hole.
Oh, wow.
And then, if you zoom out far enough, they serve as the blueprints for the fabric of the universe itself.
I mean, it sounds like pure science fiction or, perhaps a really profound philosophical revelation.
Yeah.
Finding this universal Rosetta Stone that somehow translates the deeply subjective, chaotic experience of being alive into the cold, hard, objective physics of space-time.
Well, welcome to today's deep dive. We are going to explore a really fascinating, highly technical slide deck that attempts to do just that. Our mission here is to bridge the seemingly mystical neuroscience of the 1990s with the incredibly rigorous mathematics of modern quantum gravity.
Right. We're exploring the possibility that human consciousness, the fabric of space, and a black hole's core might just be different metaphors for the exact same underlying architecture.
Exactly. So, for the open-minded and technically curious among you, okay, let's unpack this. We're starting right at slide 1, and we're going to trace how ideas that were once dismissed as fringe neuroscience have suddenly found, mathematical vindication.
Yeah, vindication in the most cutting-edge areas of theoretical physics.
So to start, let's jump back to the 1980s and 90s. There was this Mexican neurophysiologist named Jacobo Grinberg. He proposed something called the Syntergic theory. This relies on a concept he called the cosmic lattice.
Which is on slide 2 of our deck.
Yes, slide 2. Grinberg didn't view space as empty. He viewed it as this invisible, giant cosmic hologram, like an energetic, non-local matrix containing literally all the information in the universe.
And in his model, the human brain isn't just passively sitting inside this matrix, just, observing it.
It's doing something active.
Exactly. Grinberg coined the term Syntergy, which is a combination of synthesis and energy. He theorized that when a brain reaches a state of high Syntergy, meaning it achieves a really high level of internal synchronous coherence, it generates a localized neuronal field. And this field doesn't just process data, it dynamically interacts with the lattice to actively shape and construct perceived reality.
I mean, that is a massive claim. It suggests reality isn't something happening to you, it's something you are actively decoding. But the wild thing is, Grinberg didn't just write philosophy papers about this. Slide 3 breaks down how he actually tried to test this non-local connection in the laboratory.
The setup for this was wild.
So wild. So you take two people, let's call them subject A and subject B. You let them hang out, meditate together, basically build a really deep mental rapport. Then you separate them and lock them inside. Two completely isolated, electromagnetically shielded Faraday cages.
Complete isolation.
Right. Then subject A is flashed with random, unpredictable pulses of light. Subject B is just sitting in the dark, entirely unprompted.
And the results were just staggering. In about a quarter of the subjects who built that strong initial rapport, whenever subject A's brain registered the light flash, subject B's EEG showed a simultaneous spike. Grinberg called this a transfer potential. The implication was that there's instantaneous communication through a shared non-local consciousness field. It completely bypassed physical distance.
Now, I have to pause the narrative right here, because if you're listening to this and you have any background in physics or biology, your skeptical alarms are probably deafening right now. Because the human brain is famously characterized as a warm, wet, noisy environment.
Yeah, it's incredibly messy.
Right. Trying to maintain delicate quantum connections in the brain feels like trying to build a perfectly fragile house of cards in the middle of a crowded, sweaty nightclub while the bass is dropping. The environment should collapse the state immediately.
The scientific term for that nightclub effect is quantum decoherence.
Decoherence, yeah.
Thermal fluctuations, just the chaotic bouncing around of warm molecules. They destroy delicate quantum states in a tiny, tiny fraction of a second.
So it shouldn't be possible.
Exactly. That rapid decoherence is exactly why mainstream science largely dismissed Grinberg's findings at the time. The mechanics just didn't seem possible in a biological system.
But if we look at slide 4, If we put the messy biological mechanics aside for a moment, the conceptual framework he was building aligns remarkably well with physicist David Bohm's concept of the implicate order.
He suggested that space is basically an infinite folded holographic matrix of potential. And in that framework, the brain is acting as a hyper-complex distortion mechanism.
A hypercomplex distortion mechanism. Say more about that.
Well, what's fascinating here is the mechanism of perception being proposed. Your brain doesn't act like a camera passively recording a pre-existing physical world. Instead, your neuronal field acts as a biological rendering engine.
Oh, wow. Like a video game engine.
Sort of, yeah. It takes the infinite, non-local, unstructured information of the lattice and actively decodes it, forcing it into a discrete, measurable structure.
So the objects on your desk, the colors of the room.
Yeah, and even the feeling of your own ego, your sense of being a separate self, those are all just the final projected interpretations of this non-local algorithmic processing.
But so if our brains are essentially holographic decoders manipulating a field of information, how does mainstream physics actually deal with that?
That naturally brings us to the historic 1994 Consciousness Conference, which we see on slide 5.
Scientists gathered to ask exactly those kinds of questions. And they were massive questions. They were asking, does consciousness play an active role in resolving the Heisenberg uncertainty principle? Are we truly separate biological entities, or are we just localized nodes operating within a universal vacuum field?
And to even begin approaching those questions, physics had to undergo a massive paradigm shift. Researchers realized they had to move away from looking at fragmentary particles like protons, electrons, quarks as the fundamental building blocks of the universe.
So if not particles, then what?
They had to pivot to a new era where information itself is the fundamental explanatory concept of reality. Particles are really just the states that information takes.
Okay, here's where it gets really interesting, because slide 6 introduces the synthesis matrix, and this pivot to information theory is the bridge.
It is the absolute core of the deck.
Right, because this research maps Grinberg's 1990s subjective, almost mystical theories directly onto the objective math of modern quantum gravity, piece by piece.
Yes, they call these conceptual isomorphisms.
Meaning two highly complex structures map onto each other perfectly, right?
Exactly. The precision of this translation is what makes it so compelling. So Grinberg's concept of an energetic lattice maps mathematically to what modern physicists call bulk spacetime in AD-SCFT correspondence.
Okay, let's make sure we actually understand that jargon, because AD-SCFT is a huge deal in string theory. It's basically the idea that you could perfectly describe a three-dimensional volume of space, the bulk, by only looking at the mathematics of the two-dimensional boundaries surrounding it. I've heard it described like knowing every single ingredient and temperature of the soup inside a can just by reading the 2D label on the outside.
That's precisely it. The 3D reality we experience is mathematically identical to a 2D information boundary.
Okay.
And within that framework, the localized system, what Grinberg called the human brain, is mapped mathematically to a near-extremal black hole.
A human brain is mapped to a black hole.
Mathematically, yes. The brain's localized processing field, the neuronal field, maps to boundary-conformal field theory. And the act of subjective experience itself is mathematically translated as entanglement entropy.
And wait, that actually solves the Faraday cage experiment, too, because that spooky transferred potential telepathy stuff. The slide maps that directly to EPR, which, if we break that down, means that quantum entanglement, the EPR paradox, where two particles communicate instantly, is actually achieved through microscopic Einstein-Rosen tunnel. The particles aren't communicating faster than light. They are literally connected by a microscopic tunnel in the fabric of space. Replica wormholes.
It is just a stunning set of isomorphic mappings. The subjective experience of consciousness and the objective mechanics of a black hole share the identical mathematical blueprint.
Okay, so reading through this translation, I have to ask the obvious question.
Let's hear it.
Are these just really convenient, poetic metaphors? Or are these researchers implying a literal syllogistic conclusion here? Are they saying that a human brain and a black hole actually process information using the exact same physical mechanics?
Well, to answer whether a brain and a black hole are mechanically identical, we have to completely dismantle our traditional understanding of gravity. We have to stop looking at gravity as a fundamental pulling force exerted by matter. We have to start looking at it as a thermodynamic reaction within an information grid.
Which brings us to slide 7 and the groundbreaking work of physicists like Erik Verlinde and Jorma Michaela. Because back in the 1910s, physics was obsessed with finding the microstructure of matter, which gave us quantum mechanics.
Right.
But today, physicists like Verlinde are hunting for the microstructure of spacetime itself.
And their profound conclusion is that gravity is basically an illusion. It's not a fundamental force. It emerges purely from thermodynamics. It emerges from how information is stored and processed on the underlying quantum grid of the universe.
And slide 8 actually gives a specific information formula for this. It's n equals a times c cubed over g times the reduced Planck constant.
Right, and to translate that math for you, it basically means energy is divided evenly over n bits on a holographic sphere.
Okay.
And when you combine this information density with Einstein's EMC squared, you derive something called the Unruh temperature.
The Unruh temperature.
And through thermodynamics, that specific temperature directly derives Newton's law of gravitation, proving gravity is just an entropic force.
So to understand how a temperature creates gravity, slide 9 shows us this graph of the Unruh phase transition.
Yeah, imagine a microscopic system at absolute zero. It holds exactly 1 bit of information. It's completely flat. There is no gravity at all.
Huh.
But as thermal energy increases and hits that Unruh temperature threshold, the system undergoes a massive quantum jump. It's a vertical spike in energy on the graph, creating what physicists call a mass gap that protects the core of the information from annihilation.
So what does this all mean for how we actually experience gravity? Because we usually think of gravity geometrically, right? Like a heavy bowling ball sitting on a trampoline, warping the fabric of space.
That's the classic Einstein visual, yeah.
But Verlinde's theory is thermodynamic. It's entropic. So instead of the trampoline, imagine a long, complex polymer chain, like a strand of DNA or a rubber molecule. So if you grab the ends of a curled up rubber molecule and stretch it out into a straight line, it naturally wants to snap back and curl up again. But it doesn't snap back because there are tiny mechanical springs inside it. It snaps back because of entropy. A straight line is only one highly ordered state, but a tangled, curled up ball has millions of possible random states. The universe fundamentally prefers high entropy. It wants to be in the messy, curled-up state.
It always wants to maximize possible information states.
And that urge creates a physical pulling force. Gravity is exactly that. It is the thermodynamic exhaust of an information grid constantly trying to maximize its entropy. Space-time heating up and expanding.
Gravity is the exhaust of an information engine. And, recognizing that completely overhauls our view of the universe's most extreme objects.
Black holes.
Black holes. Slide 10 compares 2 views of gravity. The traditional view is an inside-out model.
Right, an extremal monopoly. An impossibly dense point of matter in the center, exerting a pre-existing gravitational force outward.
Exactly. But Verlinde's emergent gravity gives us an outside-in model. In this new model, the core is not a dense point of matter at all. It is a localized region of extreme maximum information density. The gravity we feel isn't radiating from a singularity. The gravity is just the entropic reaction of the surrounding space-time fabric trying to cope with that massive, localized clump of data.
That is wild. And slide 11 shows how this changes everything about how a black hole ages. We're looking at the long tail of the page curve here.
Yeah, because contrary to the popular belief that black holes eventually just rapidly evaporate and explode,
Which is what I always thought.
near extremal black holes, ones that are spinning rapidly or highly charged, they hit what is called the extremality bound.
And that extremality bound basically means the black hole is stuffed with the maximum possible amount of information, right?
Great.
But it has almost zero excess mass energy left to actually radiate that information away. So its evaporation slows to an absolute crawl. We are talking about timelines that stretch across trillions of years.
Trillions of years, it enters a phase of frozen decay. The black hole becomes this tiny, highly entangled remnant. And because the laws of quantum mechanics dictate that information can never be truly destroyed, the black hole must slowly trickle out its data in a phase called purification. It emits incredibly faint radiation over billions and billions of years just to keep the underlying math, the S-matrix, unitary.
It's basically the universe meticulously balancing its quantum checkbook. And slide 12 explains the anatomy of this phase. To hold on to that information for trillions of years without it leaking out, the black hole horizon acts as an incredible information buzzer.
Right, surrounding the high-entropy core is a throttle hovering near absolute zero.
So it's freezing.
Freezing. And because it's so cold, there is virtually no thermodynamic pressure to expel the data. It acts as this massive high-capacity battery with just a microscopic pinhole drain.
And then just outside that throttle is the extreme gravitational redshift. Because any quantum bits trying to escape have their wavelengths stretched toward infinity. This acts as a literal firewall, protecting the internal state, the island of information, from the external universe.
The information is held in complete suspended stasis.
Okay, I have to push back here, though.
Go for it.
Because the math is elegant and the concepts are mind-blowing. But if this is the reality of our universe, if the cosmos is literally littered with these dying quantum cores, these near-extremal black holes acting as giant information batteries, slowly purifying their data over trillions of years, why don't we see them?
That is the big question.
Why don't we look up at the night sky and observe these faint quantum stars everywhere? Where is the actual visual empirical proof?
Well, that is the million-dollar question, and it brings us to slide 13 and a very humbling reality about how theoretical physics operates today. The visual on the slide shows a scale heavily tipped toward theoretical models and away from observational data. We are currently living in an era of massive mathematical surplus. Our ability to construct perfectly consistent, mathematically rigorous models like island formulas and entropic gravity has completely outpaced our observational technology.
So we have these incredibly detailed maps of territories we just haven't built the ships to sail to yet.
Beautifully said. And this raises an important question about how we do science. Should we trust theories without immediate visual proof?
Right, it feels risky.
It does. But if we look at the history of physics, mathematics has a staggering track record of predicting reality decades before our instruments catch up. In 1964, Peter Higgs and his colleagues used pure mathematics to predict the existence of the Higgs boson, which gives mass to everything. But we didn't actually build a machine powerful enough to find it, the Large Hadron Collider, until 2012.
Nearly 50 years later.
Yep.
And Einstein used his math to predict gravitational waves back in 1916. We didn't have the laser interferometers precise enough to detect those ripples in spacetime until 2015. So the lack of visual proof today doesn't invalidate the math. It just highlights the limits of our current tools.
Until we can build instruments capable of observing the subtle quantum signature of a decaying black hole horizon, these conceptual isomorphisms remain our best, most rigorous guide to reality.
And that brings us to the conclusion on slide 14. This research brings everything full circle. Whether you are viewing reality through the subjective, organic lens of Jacobo Grinberg's mystical neuroscience, or the cold, hard, objective thermodynamics of Erik Verlinde's emergent gravity, the fundamental architecture remains identical.
Reality is a holographic construction. And if we connect this to the bigger picture, the final takeaway is profound. Space-time geometry is not an empty stage where things happen. It is simply a map of where the universe hides its information.
That is just staggering. So, to summarize this incredible arc for you, we started with 1990s experiments putting people in Faraday cages to test non-local consciousness. We translated that subjective idea into the highest levels of modern quantum gravity, realizing that our own brains might process data mathematically, exactly like near-extremal black holes. And finally, we redefined gravity itself, not as a mechanical force pulling things down, but as the entropic exhaust of a cosmic hard drive processing an infinite lattice of information.
It forces a complete paradigm shift in how we understand our place in the physical world.
Because understanding this, it doesn't just change how you view some distant black hole light years away. It changes how you view your own waking perception right now. Every single time you look at a coffee cup on your desk or look at your own hands, your brain is actively decoding the universe's hidden information lattice. You are the algorithm collapsing infinite potential into a discrete reality.
We will leave you to mull that one over.
Thanks for joining us on this deep dive.